title, two topics. The first one, Fibonacci formula. Yeah. So we use the verification way. Yeah. Verification. Yeah. Second topic, linear recurrence relations. We use the discovery way. So there are two ways we will use to show Fibonacci formula is correct. Yeah. The first way, verification way. Second way, discovery way. Yeah. All right. D.1, verify Fibonacci formula. But we'll only do special cases. General case, we will do next part, D.2. All right. So repeat our problem, original problem. But we need to get a Fibonacci formula first, because we do verification. So we need to have the formula first. All right. The formula, look at this form. Not quite normal, right? Yeah, because we know Fibonacci of numbers must be all integers. But in your formula, you have 1 over root 5. Yeah, root 5, this is an irrational number. 1 over root 5. Then you times parenthesis phi, golden ratio. Golden ratio is another irrational number. Rational, irrational number. So phi to the n minus -1 to the n over phi to the n. Okay. Yeah. So here, so you can see here, I talk about the numbers, rational, irrational numbers. Yeah. So here, let me explain a little bit. Yeah. So the rational, although the basic knowledge you should have a little bit. So here, in real numbers, these two, the rational, so you know real numbers. Yeah. Real numbers. Inside real numbers, there are two types of numbers. The first type, rational. Second type, irrational. All right. So the definition of rational, irrational numbers. So here we only need to give the definition of rational numbers. Yeah, because the complementary part is the irrational. Yeah. All right. So for the real numbers, what are those numbers? We can call them rational numbers. Yeah. So there is a special property here. So for any real numbers, here let's only look at the So any real numbers, So if I use not real, rational, real. Let me use R. Okay. Yeah. If R is a rational number, then R can be represented as a ratio of two integers. Let's say m of n, but these n all integer. Okay? Yeah. If a real number can be represented as a ratio of m over n, then we call it rational number. In other words, when we describe irrational numbers, irrational number cannot be represented as a ratio of two integers. For example, we know square root of 2. Square root 2, right? Root 2 is an irrational number. So nobody can represent root of 2 as m over n. Yeah. So in a discrete math, you have a chapter as number theory, right? Number theory chapter. And in your number theory chapter, there is a section, subsection talking about this. And you have a question. Yeah. You need to prove why root 2 cannot be represented as m over n. Yeah? So there is an example. Yeah. So you use contrapositive method. If it can be represented as m over n, then you take square both sides. So 2 equals m squared over n squared, then you can get a contradiction. Yeah. Yeah. So that's the, yeah, here. All right. But here, look at this. In our formula, we have some relatively complicated formulas involving some irrational numbers. Root 5, phi, yeah, after certain operations, suddenly they become integers. Yeah, it looks like magic. Right? Yeah, it looks like magic. Yeah. Yeah. But the first thing here, we need to show this formula is correct. Correct. Yeah. Yeah. Here you can see, yeah, it may not be that easy. Yeah, you need to do quite some work. Yeah. So here, I will use the mathematical induction to prove it here. Yeah. Because how can you verify it? Right? How can you verify that this formula is true for all positive integer n? So we need to use mathematical induction. This is a perfect place to use mathematical induction. Okay, all right. So based on mathematical induction, there are 3 standard steps we need to follow in order to apply mathematical induction. The first step, verify the base cases. Base cases. Yeah. Verify that this formula is correct for these 2 base cases. That's very easy. Yeah. So we can quickly do the verification. Yeah. When n equals 0, yeah, so it's trivial. So phi to the 0 is 1 minus 1 over 1. So the whole number inside parentheses must be 0. Yeah, so it's 0. Yeah, it's correct. Yeah. Step 2, verify for n equals 1. Yeah, here we need to do some calculation. Yeah. So let's plug in the phi number. Then, but here the second term, 2 over 1 plus root 5. Yeah, so we know in this situation, people apply a special technique, rationalize the denominator, right? Yeah. So this one we can represent as root 5 minus 1 over 2. Yeah. You know, so here we use a simple technique. Yeah. You know, multiply the conjugate, right? Yeah. You know, so here, root 5 minus 1 root, yeah, so here, 5 minus 1, right? Yeah. Yeah. So when multiply numerator, denominator, the same number here. So then after simplification, 4 at the denominator, 2, cancellation. So 2 left at the denominator. So numerator, root 5 minus 1. Yeah. All right. Yeah. So if you use this number, so then this minus 1 cancel out. So 2 root 5, that 2 and 2, 2 before root 5 and new denominator 2 cancel out. So then you have root 5 cancel out. So the answer is 1. So you verify the second base case. Second base case. Yeah. So you just, do the work carefully. Yeah. So You can get it easily. Yeah. All right. So for the mathematical induction, these two steps are already enough. Now, we do not need to do more verification. No, already enough, good enough. Why you say it's enough, right? So here, let me ask you a question. Why you say if we only verify two base cases, it's enough? Now, can you tell me? Why not three? So two is enough. One is not enough. Two is enough. But three more than necessary. Yeah. The reason is, the answer is, you look at your recurrence relation here. Your recurrence relation at the right-hand side, you only have two terms, right? Yeah. So the subscript n minus 1, n minus 2. Two lower than this n, right? Yeah. So that means you need two base cases. If I add the term f n minus 3, then you need to verify three base cases. Okay? Yeah? If I add one more term, that 2 is not enough. So you need to verify, another. Yeah. All right. Things like this. Yeah. But the next step, I want to show you some calculation techniques related to golden ratio. Now, golden ratio is a special number. So when you do the calculation involving golden ratio, sometimes you can apply its special properties. There are some special properties for the golden ratio. So now let's practice some special properties of golden ratio. So the third example, so I do another verification, unnecessary, but as some practice. Yeah. All right. So the third one, so phi squared, 1 over phi squared. Yeah, we can do expansion. Yeah. So we can do expansion. Yeah. So we already did, transformation, right? Yeah. So, and we are familiar with the formulas. Square of some formulas, right? Yeah. So we apply that formula. So then after cancellation, simplification, we get a 1. Yeah. All right. So that's when n equals 2. Unnecessary. Yeah. All right. But this one still, in this case 3 verification, I didn't apply any special property of golden ratio. I didn't. Yeah. So because it's not too hard. Not too hard. All right. The next one, I will apply special properties of golden ratio. Yeah. Because next one, it could be quite complicated. Yeah. Yeah. So if we do not apply golden ratio properties, then our computation could be relatively hard. Yeah. So we need to find a different way to do the verification. All right. Continue verification. Case number 4. This time, phi cube. Yeah. So calculate the phi cube. Yeah. So we do not want to do the, straightforward calculation. No. So here we will take, some smart way. Yeah. We want to use some smart way to do the calculation, simplification. All right. So the problem, because the degree of golden ratio expression becomes higher and higher, right? So if the degree is high, then the calculation is hard. Yeah. So our idea is very simple. We want to bring down the degree. Bring down the degree. Make the degree lower. How can you make it lower? Apply the special properties of golden ratio. We can make the degree lower. Special properties. So what? Yeah. So how to reduce the degree of this phi cube? Properties. Here, let's talk about special properties of golden. There are two properties of the golden ratio. The first property, 1 equals phi squared minus phi. Later I will show you how to see it, right? So this is our first property. 1 equals phi squared minus phi. It's 1. Second, phi squared equals phi plus 1. You can see, actually, the second property comes from the first property. So you just move this minus phi to the left-hand side. Then you switch left-hand side and the right-hand side. You get a second property. So essentially, they are the same property, but they will be used in different situations. In one situation, because when you have 1, you want to replace 1 by phi squared minus phi, then you use the first property. If you want to replace phi squared by phi plus 1, then you use second property. For different situations. All right. But how to see it? So very easy to see it. First, we just need to ask ourselves, how does golden ratio come from? So we have one quadratic equation by solving. So solving a special quadratic equation, this one, x squared minus x equal minus 1 equals 0, and the phi is a root of it. If phi is a root, when you plug in phi in this quadratic equation, you get an equality, right? You get equality. So this one, you just move some of the terms, you can get a basic property. That's simple. Okay? All right. Now, we can work on this phi cube expression. Phi cube, our goal, we want to bring down the degree of this expression. Now, how to do it? Let us split this phi cube as phi times phi squared. Same thing. But in different view. Okay? Different presentation. But the same content. And here you see phi squared, right? We make phi squared stand out. When we see phi squared, we can apply second property. Replace phi squared by phi plus 1. Then the degree becomes lower, right? Because degree of phi squared is 2, degree of phi plus 1 is 1, right? Highest degree term is 1. So you change from degree 2 to degree 1. So going down. All right. So now, we do the, replacement. Then, so after we, get this phi squared plus phi, you see another phi squared. Another phi squared. So we do another substitution. So you get a 2 phi plus 1. That's good enough. Because you bring down from degree 3 to degree 1. This expression, the highest term degree, only 1. That's good enough, right? Because you cannot bring down to 0, right? Nobody can make a degree 0. So we can stop, for this small step. Next step. Because we have 1 over phi cube term. This time, the degree, the high degree term appears at the denominator. So when we bring it down, we need to do operations differently. So let's work on this 1 over phi cube term. Now you can see in this situation, new situation, the numerator is 1, right? The numerator is 1. Okay? 1 appears in our first property, all right? Yeah? So let's replace 1 by phi squared minus phi. Okay? Yeah? Because after this substitution, there is a common factor phi between numerator and the denominator. Common factor. So we can cancel out the common factor. Cancel the common factor. All right? Yeah. After cancellation, yeah, phi minus 1 over phi squared. Yeah. You can see the degree of the denominator term going down a little bit. Yeah. Yeah. It works. But still, degree 2, still too high. So we want to make it smaller. Yeah. We need to do another step, make it smaller. Yeah. So the next step, yeah. Yeah. You can see there is another one here. Another one here. Yeah? You see, when you see one, yeah, you can apply this first property another time. Replace 1 by phi squared minus phi. All right. After that substitution, simplification, so you can see another common factor phi between numerator and denominator. So you can do another round cancellation. After cancellation, you get a 2 over phi minus 1. Now, the degree of the denominator term becomes phi. Yeah. First order, it should be good enough, right? First order. Yeah. Yeah. All right, yeah. Now, we can calculate phi cube plus 1 over phi cube. So these two expressions, -1, +1 can be canceled out. Yeah? So we get a 2 times parenthesis phi plus 1 over phi. Yeah. Yeah? So this inside parenthesis, that part corresponds to F1, right? Yeah? Fibonacci number of degree 1. Yeah? F1. So here, F3. So left-hand side corresponds to F3, right-hand side corresponds to F1. Because if we multiply 1 over root 5, both sides, we get F3 equals 2 F1, right? Yeah. That can be verified easily, right? Yeah. Yeah. So because we can calculate F3, if F3 equals F1, then you know, yeah, actually, yeah. So this formula tells us, you know, it means, this formula means F3 equals 2 times F1. F1 is 1. So, but from this formula, we can find F3 should be 2. Yeah. So we do not, yeah. So we calculate Fibonacci number F3 from this formula. We get a 2. That's the same as we calculated from the original recurrence relation, right? So 2 different ways. So here, 2 different ways to calculate F3. One way using this formula. Another way using the recurrence relation. And then these 2 ways point to the same number. Yeah. So that's our verification step number 4. Yeah. Yeah. Here the purpose is I want to introduce the how to use the special properties of golden ratio. Yeah. Because in our general verification round, we have a general round. We need to apply these 2 properties. Yeah. So get ourselves familiar with the basic properties of golden ratio. Yeah. All right. So we complete this step. So now we are ready for D.2 verify Fibonacci formula for the general case. Yeah. All right. The general case, this time, yeah. So this is the key step of the mathematical induction. Key step. We complete step 1. Now we need to do the step 2. Then step 3. All right. Powerful tool, mathematical induction. All right. So based on mathematical induction, yeah. So the step 1, check the base cases. We did it. Yeah. We completed. Yeah. But step 2, now we need to do that step 2. Step 2, we make induction assumption. Induction assumption. All right? Yeah. All right. So assume that the formula is true for when k is in the range greater or equal to 2, less than or equal to n. Yeah. Yeah. Less equal. Yeah, because we verified that k when n k equals 2, it's true, right? Yeah. In the D.1. So we will verify. We verified 2 and 3. Yeah. So here, currently, our range could be, at least this n we can, so 2, 3. We know we are 100% sure when k between 2 and 3, the current formula is correct, right? Yeah. Actually, so this step, this range, we use at this point, right? Yeah. Because we know when n equals 2 and 3, this verification is not necessary, right? Yeah. So these two cases, verification not necessary. Not necessary. Yeah, right? Not necessary. Redundant. Yeah. We can skip. Yeah. All right. Yeah. But if you skip for these two cases, then in the range for our induction assumption, so we should change to 0. And the n is true. N is true. Yeah. So we know this range is true for is 1. 0, 1. Correct. So our initial range, yeah. So for us, we know it's correct when k is in this range between 0 and 1. Yeah. So now we know, because 0, 1 we already verified. So now we know actually we can change it between 0 and 3. Yeah. So now we know this range a little larger, but actually, we don't need that large. Okay. Yeah. This large is enough. Okay. Yeah. So this large is enough. Okay. All right. Yeah. So induction assumption. So assume that the formula is true in certain range. Yeah. So here we only need to make sure the range is not empty. If range is empty, then we can do nothing. We can do nothing. Yeah. So here the only thing, the main point in this induction assumption is the formula is true in certain range, but that range is not empty. That's what we need. If it's not empty, we can get something useful from non-empty set. If it's empty, you cannot grow empty set, right? Empty, it is empty. You cannot grow. If it's non-empty, then we can grow it. We can keep growing from a non-empty set. That's the idea. Empty, you cannot grow. Nothing inside. You cannot grow. Okay? Yeah, that's the main point. Yeah. All right, so here, non-empty, right? So we can grow it. All right. the question. Yeah. So here we assume it's correct in this range. All right. In this range, yeah. Certain range, non-empty range. Step 3, we need to enlarge the range by growing. Yeah. So, all right. Step 3, verify that when when k equals n plus 1. So here, yeah. So here we use n, the subscript. We use n plus 1. So for that k, you can see first n plus 1 is out of the range, right? N plus 1, k equals n plus 1 falls outside of this range. Out of this range. Yeah. But we can show it. So here, show that. So we can show when k is 1 more than the upper bound of the range, n plus 1. Just 1 more. 1 higher than the upper bound of the range. We have the same formula. Yeah. We still have it. But we need to show it. Okay? We need to verify it. We need to show it is true. Yeah. So in this way, you can see basically what we are going to do. We just grow the range, right? We enlarge the range. Yeah? Because the upper bound, when we start, the upper bound of the range is n. After this step, can we change the upper bound from n to n plus 1? Because after we show it is correct, we can enlarge the upper bound of the range. Okay? Yeah. After another step, enlargement, we can change upper bound to n plus 2, then n plus 3, n plus 4. Keep going to infinity. How about that? Yeah. So if we can enlarge the range to make upper bound go to infinity, then we can prove it. The formula always true. Yeah, because the upper bound is infinity. So the formula is always true, right? That's the main idea of mathematical induction. All right, yeah. So here you can see we only need to do the last step, verification, the critical step. Yeah. All right, so let's do it. Yeah. Our goal, we verify this n plus 1 subscript case. Yeah. How to show it is correct? Okay, yeah. All right. So let's formula transformation here. All right. We start with the recurrence relation. Yeah, yeah. We can use it, right? Yeah. Yeah. This recurrence relation is always true, so we can use it anyway, right? Yeah. So let's apply recurrence relation. Yeah. Then, next step, the right hand side, f sub n minus 1. Yeah. You see, the right hand side we can apply the formula, right? Yeah. So we can apply the formula. And for the subscript n and n minus 1. Why we acquire this formula? Based on induction assumption, n is in the range, right? Yeah. Because here, we know the range is k. All right? Yeah. So here, k equals n in the range, right? This second term, k equals n minus 1, also in the range, right? Yeah. Yeah. Why we can use the formula for the first term? Yeah, because k equals n in the range, in this range. Why we can use the formula, this formula for k equals n minus 1? Yeah, because it's in the range. All right? it's in the range. Yeah. No. Then, now, this new expression, yeah, relatively long new expression. But we want to see if this new expression equals our target expression. This is our target expression. Okay? Yeah. Because this long expression looks different from our target expression. Yeah. But can we apply some algebraic operations to show these two expressions are the same? Then we are done. No, then we are done. Okay? All right. Yeah. Next question. How to show these two expressions are the same? Yeah, so here. Because at this point we don't know, right? So we put a question mark here. We don't know. Yeah. So we need to, do appropriate algebraic operations to convince people they are the same. Yeah. All right. Yeah. The question, how to see they are the same? Yeah. Not that obvious, right? Yeah, it's not that obvious. How to see they are the same? Yeah. All right. Now we compare the structure. So let's just do some cleanup work. Yeah. Before we do comparison, yeah, our goal, we want to do comparison. Before we do comparison, let's do some rearrangement. Yeah. All right. Yeah, because the original expression too messy. Yeah. Too messy. So we want to rearrange the terms to reveal the structure better. Structure better. Yeah. So yeah. Now you can see the expression. Non-fractional expressions, right? Yeah. So or integral expression. Yeah. But the second part, fractional expressions, right? Yeah. They have different structures. Yeah. So the first part, integral structure. Second part, fractional structure. They're different. Here also two parts. Yeah. Integral structure, fractional structure. When we do comparison, yeah. So based on our understanding of the natural world structure, yeah. So how do you understand the natural world? How things work in the natural world? Yeah. Do you have any idea things work? So how things work in the natural world? So sometimes we need to apply our understanding in the natural world. Yeah. Can you understand the natural world in this way? Yeah. Yeah. If two objects are the same, yeah. So here, because our goal, we want to see these two objects in different forms. Their outside forms look quite different, but their internal content is the same. Internal content, the same. Yeah. All right. How to see that? So when we do comparison, yeah. First, 1 over root 5 we can ignore, right? Because both sides they have 1 over root 5. Let's ignore it. Let's only compare the content inside parentheses. Inside parentheses. But inside parentheses, when we do comparison, should we compare the integral part, fractional part separately? Separately? Yeah. Because if two objects are the same, their corresponding components should be the same, right? Yeah. Yeah. So that's based on our understanding of the natural world. Okay? Yeah. Yeah. Think about if two animals are the same, but each animal has different components, right? Head, you should compare head with head. Okay? Body with body. Okay? Feet with feet, things like that. You should not compare head with feet, you know, body with tail, things like that, right? Yeah. So here we compare, you know, the components with the same structure. So that's our understanding of the natural world. Okay? All right. Yeah. So our goal, yeah, we want to, yeah, so here. So this place, we don't know if this equality true or false. So I just put a question mark here. Yeah. So that's our target, our goal. Okay? We want to see, we hope, we wish they are the same. Okay? Yeah, they are the same. We wish, yeah, here also, we wish these two equalities are true. Okay? Yeah? All right. So now, to see they are true, yeah, we use backward thinking. Yeah? So let's do the backward deduction. If it is true, what can we get? All right? Yeah, that's it. You can see after cancellation, can we do cancellation? Both sides? Yeah. So the both sides we do division by phi to the n. How about that? Yeah. Both sides division by phi to the n. Then we get f phi squared equals phi plus 1. Is it our second property? Second property of golden ratio? Yeah, that's correct. Yeah. So now we know this is correct. Okay? It's correct. Yeah. So we can multiply phi to the n minus 1. Yeah, sorry. Yeah. So here phi to the n minus 1. Yeah, not phi, sorry. Some didn't make, you already see it. Yeah. Do division by phi to the n minus 1. Yeah. So here we start here, you can see we start from the second property, then we multiply both sides by phi to the n minus 1, so we can get that. Okay? We can see it is correct. Because we know this is correct. Then we multiply the same expression both sides, so we get this expression. So we see that this one is correct. Okay? All right? That's the first part. Second, this time we need to compare the fractional component. All right? Yeah? Yeah. It is a little harder. Yeah. It looks, a little more complicated. Yeah. All right. So let's do the work. Yeah, comparison work. All right. Yeah. Backward thinking. Yeah. So if this is correct, how far can we go? Right? We do the deduction in a backward fashion. Yeah. All right. Yeah. So then remove common denominator, right? Yeah. So we can remove the common denominator. After we remove common denominator, we get this expression. Yeah. Then this -1 to the certain power form, quite annoying, right? Quite annoying. Yeah. Distraction. So we want to remove the distraction. Yeah, because remove the distraction. So we want to multiply certain power of -1 to remove the distraction. Yeah, so let's multiply both sides by -1 to the n minus 1. Both sides. Yeah. So after simplification, we get 1 equals phi squared minus phi. Yeah? That's our first property of golden ratio, right? Yeah? So this is our first property. This is our second property of golden ratio. Okay? Yeah? Yeah. So see, yeah. We know it is true, right? Yeah? First property, it is correct. Yeah. Then we do backward deduction if this equality is correct. Now we can go forward, right? Going forward. Yeah. So because you multiply both sides, so this is correct. Yeah. Then we can going forward another step, common denominator, right? Yeah. So that is correct. So then both components comparison, correct. Yeah. So the whole thing, yeah. So the whole formula, the starting point is correct. Yeah. The starting, this is correct. Yeah. Yeah. Because after that comparison, our conclusion, so this final formula, this one is correct. Yeah. If that is correct, our conclusion, remember, we can extend the upper bound of the range, correct range, true range for K infinite many times. Yeah, so then no upper bound, right? That means no upper bound. Yeah, you can always enlarge your range by extending the upper bound. Okay. Yeah, so always true. The whole formula is always true. So we complete the verification. Yeah. All right, yeah, so that we finish this topic. Yeah. Then the next topic, our second and also the last topic, deep on 3. Yeah. But deep on 3, so we need to solve linear recurrence relations. Yeah. Linear recurrence relation, there are two parts. Yeah. Two parts. Yeah. First part, first order. Second order. All right. Yeah. Yeah. Today we at least we complete the first order part. Yeah. So if we have some time, we can. Definitely we cannot complete the second part, but we can do preparation. We can do preparation for the second part. Yeah. All right. So let's look at the first order case. First order, remember, we have one question left from our previous lecture, unanswered. The topic, think about that, Tower of Hanoi problem. The formula, we haven't developed the formula. The number of disk moves for n disk Tower of Hanoi problem, what's the formula? We haven't do that. Yeah. So now we do it right here. Yeah. All right. So let's recall the recurrence relation. The number of disk moves, the capital C function, number of disk moves. Base case, C of 1 equals 1. When you have one disk, so you need a one disk move. That's very simple. Yeah. But for the general case, C of n equals 2 times C of n minus 1 plus 1. Yeah. Based on our algorithm, okay, the steps in our algorithm, we have this recurrence relation. Now, the goal, we need to find the formula for capital C of n. This is a first order recurrence relation. Yeah. Why first order? Yeah. Why first order? Yeah. Very easy. You just look at the right hand side. Right hand side, sorry. Yeah. So you use the term C, the function C of n minus 1. One order lower than the left hand side, order n. Yeah, one lower. So that's the first order. Okay? Yeah. First order, very simple. Yeah. All right. Now let's solve this simple recurrence relation. Yeah. All right. we use the problem solving thinking. Yeah. All right. Here I want to talk about another very effective problem solving strategy. Problem solving strategy. You know, in real world applications, in many situations, this strategy is very useful. Okay, yeah. So what's that strategy? Yeah. It is when you work on a problem that is relatively hard. When you work on a problem that is relatively hard, so there is one way. You can modify the original problem to make it simpler. That strategy. Okay? Yeah? Yeah. Modify slightly to make it simpler. Okay? Yeah. So that strategy. Yeah. Oh, sorry. Yeah. I'm muted. Annoying. All right, modify to make it simpler. All right, I'll make it simpler. All right, yeah. So this strategy. All right. Yeah, yeah. So here, let's apply this strategy. Okay, all right. This equation. Yeah. How do you? Yeah. So now you are allowed to change it a little bit. You are allowed to make small change. Do not change too much. Yeah, yeah. Small change, but make it much simpler. Okay, all right. Can you see if we remove that +1, it was simpler? Yeah. Can you see that? Just remove that +1. Okay. Every time we multiply by 2. Okay. Yeah. When we calculate the current C of n, we just multiply the previous C of n minus 1 by 2. Then to get a C of n minus 1, we multiply another 2, we use C of n minus 2, and so on, right? Yeah. So here you can see, after the change, it's very easy. Okay? All right. So, yeah. So here, I may put a tilde on. Yeah, because after we remove 1, the current C won't be the original C function, right? It will be different, slightly different. So let me use a C of tilde of n equals 2 times C tilde of n minus 1. Okay? Then 2 squared times C tilde of n minus 2, and so on. Okay? Yeah, so let's do another one. C tilde of n minus 3. Okay? Yeah, now it's enough. Can you see? Yeah. You know, for the general case, it should be 2 to the k times n minus k, right? Yeah. K. Okay? Yeah. All right. Then, what is the last k? What is the last k? Yeah. The last k because we want to have C tilde of 1, right? Yeah. Inside parenthesis, when we reach the problem size 1, we should stop. But when we reach the problem size 1, what is the exponent of this power of 2? 2 to what number? Can you see it? 2 to what number? Based on the rule, okay? Based on the rule. Can you see some rule? All right. So the rule, all right? Yeah. 2 to the first. This one is 2 to the first. When you start, this is 2 to the first. Okay. Then 2 squared. So the exponent number 2 inside parenthesis n minus 2. What is the sum of these two numbers? What is the sum of these two numbers? What is the sum of these two numbers? N. That's the invariant. Remember? Yeah. In our first class, we have an example. We use the invariant concept. Here we find an invariant. The sum of the exponent number and the size of the subproblem. Subproblem. Okay? Yeah? That sum is the invariant number n. All right? The last one, all right. Last one, the sum. Yeah? So here I need to write. So exponent number should be n minus 1. Because this n minus 1 plus this n, the sum should be n. The sum should be n. Yeah. So this tilde, C tilde function, when we remove the plus 1 term, we can get an answer quickly, right? Yeah. Yeah. But we know you cannot remove a term without any consequence, right? Yeah, because it's different. Yeah. So, but there is a gap. Now we need to bridge the gap. We know there is a gap between these two versions. Yeah. Don't worry. Although there is a gap, but that gap is not too much. We can bridge it easily. Yeah. Yeah, that's the point. Yeah. So let's bridge the gap between these two versions. All right. The first version, that there is a constant term. Plus 1 is the constant term. Second version, no constant term. Yeah. So here, there is a name for it. The second version without constant, we call this version homogeneous. Homogeneous recurrence relation. No constant term. Okay? Yeah. So this version, we work on a version, it is a homogeneous version. Sorry. Homogeneous version. Our original recurrence relation, the version is a non-homogeneous version. Yeah. So it tells us we need to find a solution for the homogeneous version first. Then we go back to the non-homogeneous version. Yeah. All right. So let us bridge the gap between these two versions. What is the gap? All right. Now we need to see how much work we need to do to convert a non-homogeneous recurrence relation to a homogeneous recurrence relation. Yeah. This is the non-homogeneous version. Our goal is to a homogeneous version. All right? Yeah. The difference is this plus 1 term. Yeah. Here, can you see what kind of special operation, after we apply certain special operation, we can make that plus 1 term disappear? Is there some special way? Yeah. Because we can do some algebraic operations, right? We can do many different algebraic operations on this equality. Yeah. So what special algebraic operation? If we do it, we make that plus one term disappear. Yeah, interesting, right? Yeah. Yeah. So that's the important step in this problem solving case. Yeah. Can you see that? Yeah. Yeah. All right. Think about. Yeah. We can plus one both sides. How about that? This operation. Both sides, we add one. We can make that plus one disappear. Can you see that? Yeah. Why? All right. Because after you add that one both sides, left-hand side becomes C of n plus 1. Right-hand side becomes 2 times C of n minus 1 plus 1 plus 1, you get a 2, right? Yeah. 2. But a 2 is a common factor, right? Yeah. 2 is a common factor. So we factor that 2 out. Inside C of n minus 1 plus 1. All right. Can you see after this step, do we make the plus 1 term disappear or not? Think about that. After this step, yeah. So this is legal, right? It's a legal algebraic operation. Yeah. Nothing is wrong. Yeah. So we change the form. Yeah. After this algebraic operation, we change the form. The new form, this is a new form. But does this new form match our requirement? We want to make the plus 1 gone. Okay? Yeah. Yeah, because some of you may still not feel quite comfortable because you see plus 1 here, right? You see plus 1. Yeah. Yeah. So you are still not convinced. You make it that constant term disappear. Yeah. But don't worry. Yeah. Don't worry. Yeah. Can you replace this C of n plus 1 by another auxiliary function, d of n? How about that? You define a new d function, d of n equals C of n plus 1. Now you only need to work on the d function. So the right-hand side, 2 times C of n minus 1 plus 1. Is it another d function? D of n minus 1, right? Yeah. Equals d of n minus 1. Okay. Now you get a new recurrence relation, and in this one, the plus 1 term is gone, right? Yeah. So for this d, yeah, after you introduce a new function, d function, you make it completely homogeneous, right? Yeah, it's homogeneous. Can you apply your previous solution for the homogeneous? Yeah, because you already solved the, homogeneous version of the recurrence relation. Yeah, based on your solution, your d function, the solution, yeah, because that's 2 to the n minus 1, right? 2 to the n minus 1. Right? Yeah. Yeah. All right. Yeah. 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 All right. Yeah. So then, so you can go back. C of n plus 1 equals 2 to the n minus 8. Yeah, but here, let me see. A minus 1? Yeah, but something is a little not quite right. Yeah, because in this way, C of n equals 2 to the n minus 1 minus 1. But our formula, it looks like this should be n. Yeah, I need to check. Yeah. this place something is wrong. Yeah, 2 to the n. C of the, oh, okay. Now I understand. Yeah. Now I understand. Actually, yeah. So this D, yeah. One more step, just one quick step. So yeah, actually it's the n, right? Yeah, because D of 1 is 2. D of 1 is 2. So D of n equals times D of 1, there is another 2, so equals 2 to the n. Okay? Yeah. So D of n is 2 to the n. So C of n equals plus 1 equals 2 to the n. So here you have 2 to the n minus 1. Yes. Yeah, because initial value has been changed. Yeah. When we plus 1, we also need to change the initial value. Yeah. All right, so we run out of time. So let me stop right here. Yeah. Next time we have, the last step. Yeah, the last step, quite important. So I may need 20-something minutes to complete last portion. So then we can start module 4. Yeah. Next time. Yeah.